Thank you, Dr. B. I'm Eric Smith, Principal Investigator at Endeavour Aerospace, and today we will be presenting our system validation review of the Advanced Utility Roving Apparatus, nicknamed ARA. This presentation will include a mission summary, concept of operations, our system validation, our subsystem validation, and conclusions in programmatics. Before I begin the presentation, I'd like to introduce the rest of my team: Silas Graff, Benjamin Barr, Harold Ziegel, Blake Maddox, Angelo Cresceno, Daniel Colantonio, and although he already presented the communication portion of the project this morning, Michael Fusco, the final member of our team. Our mission is the reconnaissance operation for Guided Unmanned Exploration 1, nicknamed Rogue 1, and the mission is to deploy a reconnaissance rover from a UAV in a remote location, conduct surveillance of the area, and then return it to the original location. Here's our system of systems for the product structure tree for the system of systems. We have the Rogue 1 system of systems, which is composed of the VESTA system, the carrier, the ARA system, the reconnaissance vehicle, and the ground station system. This presentation will be focused on the ARA system. We have our concept of operations through this animation, the ground station located in this building, the Mos Eisley spaceport where we begin the mission, the Yavin 4 ruins, our target area to explore, and the hyperlane, which the carrier vehicle will travel back and forth across. First, we start out in the Mos Eisley spaceport with the vehicles integrated together. VESTA transports down the hyperlane with ARA safely secured in the payload bay on the undercarriage. Once we get outside the Yavin 4 ruins, we'll go ahead and enter phase 3, deployment of ARA. The servo motors in VESTA will release ARA so that we can roll out of the payload interface ramps and then proceed toward the Yavin 4 ruins. For phase 4, we will conduct our reconnaissance of the Yavin 4 ruins. During this entire operation, a vehicle driver will be controlling the vehicle in real time from the ground station up in the AC1 conference center, and the live data streamed from the vehicle will be recorded. Once we've conducted all of our reconnaissance, we return to VESTA for phase 5 and redock. The servo motors re-engage so that we are locked safely in place. And then for phase 6, we return to the Mos Eisley spaceport, once again flying back across the hyperlane the same way we went in. And then we conclude the mission with phase 7, which includes our post-flight operations. Based off of this concept of operations, our team developed the following primary objectives, all of which are necessary to be satisfied in order to achieve mission success. They are that the ARA system should deploy from the VESTA system in the Yavin 4 ruins, should be capable of navigating the ruins, should generate detailed images of the ruins, broadcast the images to the ground station, and perform the mission in manual mode. Our secondary objective, which is expected to be accomplished, is that we should redock with the VESTA system once the images have been transmitted. However, if we are able to successfully get all of our data, even if we cannot return, that would be considered a successful mission. We also have 3 constraints on the design of the ARA system. That is that we will only navigate the grassy portions of the Yavin 4 ruins. We have a budget of $720, and the total mission duration will be less than 60 minutes. I will note that the first constraint there was originally intended for the initial mission location, where we had both grassy and concrete portions. For those of you who were here at the earliest presentation, you know that we switched mission locations about 6 times within the last couple of weeks due to facilities conflicts. And in our final mission location, there was no grass anywhere in sight, so this constraint was essentially nullified. Here's our design structure tree for the ARA system, which is composed of the guidance, navigation and control, locomotion, structure, computation and data handling, communications, and electronic power subsystems. Here we have our concept art for the ARA system, which has 4-wheel drive powered by 4-stepper motors a video IP camera to collect the video data and relay it to the ground station, and ultrasonic sensors at the four corners of the vehicle to fill in the blind spots for the vehicle driver that are out of the field of view of the IP camera. Next, within the vehicle, we are powered by a LiPo battery. We have a microcontroller to process all of our commands. We have two motor controller boards to relay those commands to the stepper motors, and we have a modem to encrypt and decrypt our communications. At this point, I would like to welcome up Silas to talk about our structure subsystem validation.
Thank you, Barak. The structure subsystem is a partition of the ORA system and contains two components: the chassis, which controls how the ORA system interfaces with the terrain while it is traversing through the Alvin Four ruins, and the hardware bay component, which provides a mounting position for all the other subsystems of the ORA system. The structure subsystem has one objective and two critical component level objectives. Critical in this case meaning that these component level objectives have significant impact on the ORA system's ability to meet its objectives. These objectives are that the structure subsystem should allow for maneuvering within the Alvin Four ruins, that the chassis component should provide a rigid mounting position for the locomotion subsystem, and that the hardware bay component should provide a rigid mounting position for the non-locomotion subsystems of the ORA system. The structure subsystem has two critical component level requirements. These are that the chassis component shall withstand a horizontal shear load less than or equal to 20 newtons applied at the mounting position of the locomotion subsystem, and that the hardware bay component shall withstand a distributed load less than or equal to 120 newtons applied at the non-locomotion subsystem's mounting positions in the negative z direction. In order to meet these requirements, we have developed this design. It is composed primarily of aluminum sheet metal sections that have been adhered together with a high-strength epoxy. Here you can see several key features of this design, including the antenna ground plane, removable access panel, internal struts, and stress reduction brackets. Here you can see the different parts of the structure subsystem prior to being epoxied together. In order to numerically validate the chassis component requirement, we created an ANSYS workbench model of the structure subsystem. We applied the constraints and loads as described by the requirement and then observed the resulting stresses in the model. These stresses did not exceed the failure criteria for the aluminum, epoxy, or fasteners. This numerically validated the requirement. In order to experimentally validate the requirement, we took the assembled structure subsystem and applied the constraints and loads as described by the requirement. The structure did not show any signs of plastic deformation or cracking, but unfortunately we were unable to experimentally validate this requirement because we did not use any form of instrumentation to determine if the stresses in the structure had exceeded our failure criteria. In order to numerically validate the hardware bay component requirement, we created another ANSYS workbench model of our structure subsystem. We applied the constraints and loads as described by the requirement and then observed the resulting stresses in the model. These stresses did not exceed the failure criteria for the aluminum, epoxy, or fasteners. This numerically validated the requirement. In order to experimentally validate the requirement, we took the assembled structure subsystem and again applied the constraints and loads as described by the requirement. We did not observe any plastic deformation or cracking in any portions of the structure, but we were unable to experimentally validate this requirement because we did not use any form of instrumentation to determine if the stresses had exceeded our failure criteria. In summary, both requirements were successfully numerically validated, but not experimentally validated. Now I'd like to hand the presentation off to my colleague Benjamin to talk about our computation and data handling subsystem.
Thank you, Silas. So the computation and data handling subsystem lies within the ORA system and has two components, which are the microcontroller and the motor controller. The objective of this subsystem is that it should contain all the components of the computation and data handling subsystem. The critical microcontroller component objective states that it should process the ORA system sensor and command data. The critical motor controller component objective states that it should relay power to the ORA system's motors. There's only one constraint within this subsystem, and it states that the microcontroller will have an Ethernet port. This is so that it can connect to the switch component of our communication subsystem. The critical motor controller component requirement states that it shall relay less than or equal to 17 watts of power to the drive motors component of the locomotion subsystem. Here we have laid out our interfacing diagram. On the right we have our respective subsystems. This diagram is to show our information going into and out of this computation and data handling subsystem. As you can see, sensor data is coming from the guidance, navigation, and control subsystem, while command data is coming from the ground station system into the Raspberry Pi. Then confirmation data is sent back to the user at the ground station for reference. The motor controller relays pulse width modulation signals and power to those stepper motors. And this is our current design to satisfy our subsystem objectives. On the left, we have our Raspberry Pi on the bottom with the Ethernet port and two motor controllers stacked on top. Note that there are two motor terminals in which the Locomotion, the stepper motors of the Locomotion subsystem will connect to, and then separate it's called the jumper terminal, where the motor controllers will be powered separately. This is due to the Raspberry Pi not being able to supply enough current without frying the board. Then on your right, we've got the ERAU system and the respective location of the computation data and handling subsystem within. Here we have our command program flowchart. This we developed last semester, so we could start early this semester from the ground up. We had limited knowledge initially, so we literally had to start with our Python scripts, basically powering LEDs based off key inputs from the keyboard. Then we developed this into this loop here, where it continuously waits for user input, and based off of that input, it translates to forward translation, backward translation, right and left rotation, and throttle up and throttle down for the vehicle. Here we have our sensor program, which is another loop that continuously reads sensor data, ultrasonic sensor data, and prints it to a Linux terminal on a separate computer of the ground station for the user to read off of. For the validation of our critical motor controller requirement, to numerically validate it, we pulled the maximum operating voltage and maximum operating amperage from the datasheet of the chosen motor controller to calculate the maximum operating power of 40.5 watts. As you can see, this is not less than or equal to 17 watts, but by overshooting the power, we're able to scale this down to meet the requirement of the system, of the subsystem. To experimentally validate this requirement, we used a multimeter to hook up to each of the motor terminals to measure the voltage and amperage that will be going to each of the motors, and added them up, calculated the power output to be 13.76 watts, thus experimentally validating this requirement. And now I'd like to welcome up Harold Ziegel to talk about our Locomotion subsystem validation.
Thank you, Benjamin. So Locomotion is a subsystem of the ERAU system and is comprised of three components: the drive motor adapters, the wheels component, and the drive motors component. The team has identified one primary objective for this subsystem, which states that the Locomotion subsystem should maneuver the ERAU system in the Apparatus roads. And we've identified one critical component objective, which states that the drive motors component should provide torque to the wheels component to maneuver the ERAU system in the Apparatus roads. There are a set of subsystem level requirements that state that the Locomotion subsystem shall provide the ERAU system with a speed greater than or equal to 0.05 meters per second, but less than or equal to 1 meter per second. Additionally, there are a set of critical component requirements that state that the drive motors component shall provide a torque greater than or equal to 0.47 Newton meters, but less than or equal to 1.32 Newton meters. Here we see the design solution the team has developed. 4 stepper motors will be attached to 4 adapters using small set screws, which allow the 4 wheels to be attached also using small screws. The 4 stepper motors were purchased, as well as the 4 RC-style wheels, while the 4 adapters were fabricated here on campus out of 6061 aluminum. Here we see where the Locomotion subsystem is found on the ERAU system in the 4 corners of the vehicle. To numerically validate the subsystem level requirements, modeling and simulation was conducted in MATLAB, which found that the vehicle would be capable of 0.1 meters per second of speed, which falls in the desired range set forth by the requirements, numerically validating both. To experimentally validate the requirements, please play the video. ERA was timed as it covered a known distance, and this speed was found to be 0.09 meters per second, which again falls within the desired range set forth by the requirements, experimentally validating both. To numerically validate the torque motor requirements, we used the supplier specification sheet, which showed that the torque provided by the motor would be 1.80 Newton meters, which is greater than our lower bound of 0.47 Newton meters, but is also greater than our upper bound of 1.32 Newton meters. So we were able to numerically validate the lower bound, but not the upper bound. To experimentally validate the torque, a string was attached to the end of the drive shaft with a known mass on the end. The motors were started and the string was wound around the shaft, and we used until motor stall occurred, and we used that data to calculate the torque output. This was found to be 1.25 Newton meters, which falls within the range set forth by the requirements. As for the discrepancy in the numerical and experimental torque, the numerical was the maximum torque output provided by the supplier. We figured that this would be able to be scaled down, but the supplier specification sheet provided no proof of that, but we were able to find experimental proof that this was possible. But the 1.25 Newton meters was still low because the chosen motor hats were only providing 1.2 amps of current to the motors instead of the 3 amps required for a maximum torque output. So in summary, we were unable to numerically validate the upper bound of the torque requirement, but we were able to experimentally validate both the subsystem level and component level requirements. I'd now like to welcome up Blake Maddox to talk about the guidance, navigation and control subsystem.
Thank you, Harold. The guidance, navigation, and control subsystem is located underneath the ERA system, and it consists of 3 components: the state determination component, the visual sensors component, and the rangefinders component. The team has generated 2 subsystem level objectives for the Gnc subsystem. The first objective is that the Gnc subsystem should allow a human operator to guide the ERA system through the Avon ruins in manual mode. The second objective is that the Gnc subsystem should generate the detailed images of the Avon ruins as designated by mission objectives. There were 2 critical level objectives, critical component objectives that needed to be accomplished to assist in accomplishing the subsystem level objectives. The first critical component objective is that the visual sensors component should display visual data to the ERA system operator of the Avon ruins, and the second objective is that the visual sensors component should generate the detailed images of the Avon ruins. The team has also generated 3 critical component requirements to assist in accomplishing the subsystem level objectives. The first critical component objective is that the visual sensors component shall have a video resolution of greater than or equal to quarter video graphics array, otherwise known as 240p. The second requirement is that the visual sensors component shall have a video frame rate of greater than or equal to 15 frames per second. And the last requirement is that the visual sensors component shall generate images of the Avon ruins with a resolution of greater than or equal to 720p. Currently shown above is the Gnc subsystem located on the ERA system, where we see the ultrasonic sensors at each of the 4 corners of the ERA system. The video camera is located up at the front of the system, and the IMU located inside back corner of the ERA system. In order to numerically validate these requirements, we located the spec sheet of the component, the GeoVision Bullet IP camera, and we looked at its resolution specs as well as its nominal frame rate. And the numerical results were that the video camera can go to 240p, 720p, and a frame rate of 30 frames per second, thus numerically validating each of the requirements. Located off to the left is, in the red circle, is the volt IKP camera before its disassembly. And located off to the left is the disassembled pieces that were later added to the Aura system. In order to experimentally validate the requirements, what we did was we placed the Aura system pointing towards a designated wall, and then we changed the substream settings to the low settings of CIF and the required settings of 720p. And what you see here is a side-by-side comparison of the two resolutions, thus experimentally validating the experiment. In order to experimentally validate the frame rate, what we did was we took the Aura system to the M4 Ruins location, and we had it pointing to a known active center. And then what we have here is a video showing a bird fluidly flying across the screen using the mainstream settings of 1080p and 25 frames per second, thus experimentally validating the experiment. In summary, all of the requirements have been numerically and experimentally validated. I would now like to hand it off to Angelo to talk about the EPS subsystem validation.
Thank you, Blake. As you can see here, the EPS subsystem lies under the Aura system, the three major components being the battery, the power distribution board, and the power over Ethernet box. We set two subsystem level objectives for this subsystem, and those are that it should provide the electric power needed to complete the mission, as well as distribute the electric power to the other subsystems that require it. Looking a little closer at the power distribution board, we set one critical component objective, and that's that it should regulate the voltage from the battery to each component that requires electric power. Continuing on to requirements, we set one battery component requirement, and that's that it shall provide electrical energy greater than or equal to 44 watt-hours. All of the next ones, the critical power distribution board component requirements, are set ranges for the operating voltages of all the components. So we decided, based off the spec sheets, that we need 4.75 to 5.25 volts to the microcontroller, 11.4 to 12.6 volts to the drive motors, 21.7 to 24 volts to the modem, 11.4 to 12.6 volts to the camera, and then finally 4.75 to 5.25 volts to the switch component. On this diagram, you can see where all the components are laid out within the Aura system. Of note, the power distribution board is not actually shown because it's comprised of these DC-DC buck converters along the edges. This is a block diagram showing the flow of power from the battery to all the different components. Also of note with the implementation of our fuses to protect our components. Looking into the EPS power budget, you'll see all listed components with their respective subsystems. We looked on the spec sheets to see the nominal operating voltages as well as the maximum currents to calculate the maximum power draw during the mission. Applying a 20% surplus to that total of 36.9 brought us to 44 watts of power. The requirement set actually though is an energy requirement, which is measured in watt hours rather than watts from the previous slide, and that's because we needed to know how long we need this battery for. In this case, it's just 1 hour for the mission duration, so 1 times 44 gives us this 44 watt hour requirement. As you can see, the selected energy output of this battery is 99.9 watt hours, which is well above the 44, and that's also because we needed that 22.2 volts of nominal voltage to operate within all our components. To actually test this, we use the charger for the battery on its discharge setting because it allows us a constant current discharge that we set to 0.3 amps. We started at 22.2 volts and then tested it for 3 hours. We recorded the data of the voltages every 5 minutes and then came up with this plot here. The first thing you'll note is the red line on the bottom, which is the critical voltage level for this particular LiPo battery. LiPo batteries should not be discharged past 80% of their nominal voltage, as it could lead to cell rupture or fire. The next line you'll notice is the dashed black line on the right, which is the listed battery rating of the 99.9 watt hours. And the blue line being our data. We reached that critical voltage level beyond the 99.9, thus experimentally validating this requirement. To numerically validate the power distribution board requirements, again, we're stepping down this 22.2 nominal voltage from the LiPos to whatever desired output for each of the components. For the microcontroller in particular, it requires a USB input, so we found one with a USB output. In this case, it's also the range of voltages it accepts is 5 to 36 volts, and then the standard 5 volt USB output. For the rest of the components, similarly, we've stepped down this 22.2 nominal voltage using these buck converters, which utilize a linear potentiometer that allows us to set and calibrate the output voltage to whatever we need for each component. In this case, 3 to 40 volts of input, and we can set the range to 1.5 to 35 volts of output. To actually test it, we set up the subassembly of all the electric components and used a multimeter to record the output voltages of all the DC-DC buck converters. The data from those tests is shown here, and you can see all the experimental voltages lie within the required voltages set forth earlier, thus experimentally validating these requirements. So in summary, all of our requirements for the EPS subsystem are numerically and experimentally validated. And now I'd like to hand it off to Daniel Colantonio to talk about the ERAU system.
Thank you, Angelo. The ERAU system has 6 requirements which we designed to meet in order to accomplish the mission. These requirements include the ERAU system shall have a total mass that is less than or equal to 3.5 kilograms. The ERAU system's horizontal diagonal shall be less than or equal to 50 centimeters. The ERAU system shall drive down a ramp with an incline that is less than or equal to 35 degrees and a height that is less than or equal to 9 centimeters. The ERAU system shall drive forward while in a sideways height differential that is less than or equal to 9 centimeters. The ERAU system shall drive forward while a single wheel encounters a cube with a side length that is less than or equal to 2 centimeters. And the ERAU system shall drive up a ramp that is with an incline that is less than or equal to 30 degrees. For the first requirement, that the ERAU system shall have a mass less than or equal to 3.5 kilograms, we used modeling and simulation in CATIA to determine a total mass of 2.7 kilograms. After fabrication, we placed ERAU on a measurement scale and recorded a measurement of 3.2 kilograms. This mass is a lot larger than our numerical results because the stepper motors that we received weighed a lot more than what were advertised. For the next requirement, that ERAU system's horizontal diagonal should be less than or equal to 50 centimeters, we used modeling and simulation again to determine a result of 44 centimeters, and we used a tape measure after fabrication to measure 44 centimeters also, both numerically and experimentally validating this requirement. For the next requirement, that ERAU system shall drive down a ramp with an incline that is less than or equal to 35 degrees and a height that is less than or equal to 9 centimeters. We used modeling and simulation to numerically validate this. And this video right here shows that it has also been experimentally validated. For the next requirement, the ERAU system shall drive forward while in a sideways height differential that is less than or equal to 9 centimeters. We use modeling and simulation again to numerically validate this, and this video right here shows that we have also experimentally validated this requirement. For the next requirement, that the ERAU system shall drive forward while a single wheel encounters a cube with a side length that is less than or equal to 2 centimeters, we use modeling and simulation to numerically validate this, and this video also shows that we experimentally validated this. This is an example of a poorly written requirement, because although we have experimentally validated this requirement, due to the placement of the LiPo battery and the center mass because of that, only the front wheels are able to overcome this 2 centimeter cube and not the rear wheels. For the next requirement, the ERAU system shall drive up a ramp with an incline that is less than or equal to 30 degrees. This was numerically validated using modeling and simulation, and this video here shows that it was also experimentally validated. This is also an example of a poorly written requirement, because of the center of mass placement, the vehicle can only drive up the 30-degree ramp backwards and not forwards. In summary, all of the requirements have been numerically and experimentally validated. I'd like to hand it off to Barrett to conclude with conclusions and programmatics.
Thank you, Daniel. First, I'd like to show the video of our solo system validation. Because Vesta was not yet ready to fly, we ran our mission independently, and this video will go ahead and show the results at times 16 speed because this performance took almost an hour to complete. First, we deploy from Vesta, and as you can see from Ara's perspective, we head toward the Yavin 4 ruins, and then this will show a couple highlights of navigating the entire area. During this time, the live stream was collected at the ground station, and it was recorded using software on the computer. And once we had surveyed the entire area, we returned to the Vesta system and redocked. And based off of the results of this mission, all of our system level objectives were satisfied. Moving into programmatics, here's a system of systems projected budget. Of note, we were allotted $720. However, on this slide you can see our projected and actual costs. While our projected cost was under budget, our final cost was actually over budget, which meant we had to dip into the other areas of the mission which had surplus funds or reserve funds in case of emergencies. And the reason for this discrepancy is that when we had originally priced out our components approximately 4 or 5 months ago on websites such as Amazon, we saw a lot of very good deals, and by the time we actually went to purchase those components, those deals were no longer around and we had to purchase much more expensive alternatives of the same component. Additionally, there were some things such as washers, bolts, and screws that we assumed that we could get for free from the AXFAB here on campus. However, in our design, these were some of them non-standard sizes, and we had to purchase these items. And finally, during the segment of the mission where our mission environment was being moved around campus several different times, we went ahead and purchased alternative stepper motors and wheels with different diameters and tread types so that we could experiment in different terrains and know which areas would be suitable for us to run the mission. And finally, we have the Endeavour Aerospace labor hours for the entire project, totaling approximately 3,650 hours between the entire team. Now, concluding with lessons learned, first, team communication. We called ourselves the pancake team, not because we all like pancakes, but because we chose to go for a very horizontal structure in our team dynamics. Traditionally, many capstone teams have different sub-teams, each with sub-team leads, and like a very hierarchical team structure. We allocated that everybody on our team, other than myself, was in charge of a subsystem, and that decreased the lines of communication between everybody and put everybody on an equal footing, increasing the flow of ideas and communication. Second, writing requirements. We learned that you need to be very specific with your requirements to make sure that they both reflect the needs of the mission and are not satisfied in ways that you did not expect. So a perfect example of this was getting over that step height with the wheels. Originally, we were noticing that the back wheels could not get over those, and we came up with some different solutions. Some of them were not feasible without redesigning portions of the vehicle, and we implemented some of them. It got a little better, but we couldn't completely fix the problem. And then somebody said, well, technically speaking, we don't need to get all of the wheels over the step because the requirement doesn't say that. And then we realized that we didn't write a very good requirement because it was still met without actually meeting the need of the mission that we had originally intended. Next up is requirement validation. In the world of engineering, we generally prefer the quantitative, not the qualitative, and we realized when we were conducting some of our tests that the results of our tests were qualitative in nature. For instance, in the structure subsystem, We assumed originally that just observing the structure for failure at the end of our test would be sufficient. However, in practicality, that's not a sufficient way of validating that requirement because we didn't have an objective number to look at to validate that our structure had actually withhold the forces that we designed it to withhold. And finally, we learned the value of documentation. Definitely as the project became more and more complex as we went on, we needed to be writing down everything because none of us could remember all the different nuts and sizes, all the different screws, where they went in the vehicle, and having that information readily available and documented so that we could go back and fact check that was critically important. And finally, Endeavour Aerospace would like to acknowledge the following individuals and teams that assisted with our project. Specifically, we would like to thank Dr. Julio Benavides and Dr. Matthew Haslam for being our capstone instructors, and we would like to thank the panelists for taking their time to come out and watch this presentation. And at this point, I would like to invite the rest of my team up for questioning.
We have 15 minutes for Q&A.
All right, good job. Did I miss the ultrasonic sensors and how those were tested? Did I miss that, or was that not discussed?
We did not discuss that in our presentation. We chose to omit that due to time constraints. The main source of navigation, especially in the new mission environment, turned out to be the IP camera. There weren't a whole lot of closely clustered objects in there. Unlike the original mission location inside that black gate, there were a lot of things very close, and we were worried that if we tried to turn, we might run into a corner. The way that we did test those ultrasonic sensors were we used basically a wooden dowel, and we placed that at known distances away and at known angles from the ultrasonics and ensured that the reading that we were getting was correlated to that distance.
And with the environmental description, you kind of mentioned it towards the end that the requirements were probably a little sparse in that area. Was there any thought to having a description document that says what you would be able to handle and what you expected to see and what, Venn diagram was overlapped?
Good question. We did not go through the process of defining that in writing, no other than defining the mission environment that we had been designing to operate in the entire time. And then when that became no longer available due to conflicts with facilities, we looked into how would we be able to maybe adapt the wheels and or the stepper motors to drive on grass, to drive on pavement, to drive on these different surfaces that we hadn't originally designed for. Does that answer the question?
Nice job. I wanted to ask, did you guys consider any contamination concerns on for your rover in terms of its operational environments? So I see a lot of electronics that are exposed, and I also look at the mission profile. There's a lot of in terms of flight and ground operations hazards that could be encountered and damage you. Did you think about covering things up?
No, we didn't attack the problem in that perspective. We did have contingency plans in case the carrier were to crash and how to deal with that mess, but more so we were concerned with making sure that we were as light as possible for the carrier to be able to carry us across. So we didn't really attack the aspect of contamination as much, but that would have been a very interesting thing to consider. Actually, Silas, would you like to take this?
For the structure subsystem, we had a contingency plan for using a monocoat RC aircraft skin material wrap of the structure in case that turned out to be more of a problem than we were expecting. Our original analysis of the area, we didn't think there would really be enough objects that would be able to poke up into our hardware bay.
Okay. And then, so you asked part of the question, but it wasn't clear to me how you were planning to use the ultrasonic sensors and IMU really. Was that more for was the operator going to look at that data, or were there onboard software to actually say, hey, you're about to hit something, I'm going to not allow that command to be executed?
The operator was going to look at that data.
Okay.
Essentially, our camera had a very narrow field of view right at the center of this vehicle, and we were concerned that because we are so wide, with the cluster of objects in our initial mission location, we could be right next to something, and then we try and turn and bump into it, and we don't realize it's there. So we went ahead and added the ultrasonics to fill in those gaps in the field of view, and the IMU was, in the end, we used it to just provide a visual, like numerical reference for the vehicle driver that as they're clicking the command to move, there is some acceleration happening, especially because we chug along a little bit slowly, so that was just more of a visual aid to ensure that they were always aware of what was going on inside the vehicle.
Thank you.
Nice job, very
Thank you.
professional. I thought I've been seeing a lot of good lessons learned from these presentations, and I like your lessons learned on requirement writing and validation. That's really important. The Aura system objectives, I didn't see them presented. I saw the requirements, but not the objectives. So I thought another good lesson learned, of course, was the poorly written 2 centimeter cube requirement and the incline requirement, and then how you thought you'd modify that, if you were to go back and do it again, how you modify that requirement. So we can't say that the design is validated if you don't meet your mission objectives. So that's just kind of a little pick there. And especially if those requirements, you can verify them, but they'd be poorly written because they're not meeting the mission objectives. So just something to think about in verbiage. A lot of people in industry mix up verification and validation. And then, I probably missed this, but the relay power requirement, I think, was less than 17 watts. And the numerically validated value was 40.5 watts. So it's more than the requirement. Did I miss something?
Yeah, to address those things in order, as far as the mission objectives for the Aura system, we did have those. If you'd like to see them, we could go to that slide.
Sure.
Toward the very beginning, right after the mission comments. Should be about slide 5.
Okay, so it wasn't in the Aura system section.
Yeah, we
Okay.
went ahead and put them right at the beginning so that the entire big picture.
Got it, I missed that. Vesta did it different and they put those objectives in the, okay,
Yeah.
okay, that's good. So then the power.
In terms of the power, we essentially that maximum number was the maximum output that was possible for PWM signals, but we had plans to decrease that using the software. So essentially we just needed the power to be at a certain level, and although our component could produce more than that, we knew that we were also capable to have it produce anything less than that maximum level. So that's why we considered that numerically
Okay. Okay, nice job.
Very nice job. I too wanted to remark on, I thought it was a very good lesson learned in terms of requirements definition. Well, I think you're absolutely correct in noting that these requirements were sometimes poorly written. I would just caution in the future as you guys get out into the industry, sometimes it's not always the requirement, sometimes a redesign is necessary. And I'm not saying that you were too quick to jump the gun on that at all. I think your assessment's correct. Just always be willing to consider a redesign if it is necessary. But other than that, I actually don't have any questions, so I'll pass it on.
And just a little tidbit, we actually did have redesigns that we came up with. The main issue was that our stepper motors could not put out the torque that they were designed to put out, because we found out that once we assembled our entire electrical circuit, that because of our buck converters, we could either get the current that the stepper motors wanted to see or the voltage, but we couldn't get both at the same time. So we chose to decrease the voltage from 12 volts to 3 volts and give them as close to the current that they wanted as possible. But the way that we would have tackled that if we had time to purchase more components and redesign a large portion of the system was just redesign some of our CNDH and EPS subsystems to make sure that we could meet both of those values at the same time. And we knew what components we would go that route, but at the point that we were in the semester, it was just too late to implement that. And we managed to get away with performing the mission just by navigating around any obstacles that were too large for us to climb.
I'll echo everyone else. Good job. Glad there was a lot of lessons learned. You touched on it at the end there a bit, but in the structures section, you mentioned you couldn't experimentally validate because of the lack of instrumentation. Is there a reason for that?
The reason was only lack of experience on our part. When we wrote the test plans, we were not thinking in terms of making sure that we were going to have a number to compare to a number that we knew we needed to meet. We were thinking more in the qualitative mindset of like, well, if we mount the structure and then hang some weights from it and it doesn't break, then it should be good. And then when we were actually testing that, we realized that that was not a good approach for good engineering methodology because it was so qualitative in nature, and we didn't have any numbers to really back up that assessment.
Glad you at least learned from that. I just have a general curiosity. Did you ever give any consideration to autonomous guidance instead of manual?
We did. Very, very early on, we did a trade study between those two. And the reasons that we decided to go the manual route were, one, that we didn't have a whole lot of software experience, so to make sure that we could completely finish the project within the allotted time that we had, we chose to go the safe route. And for the second thing, in the original mission environment, in that enclosure, there was one, there weren't a lot of good visual callouts for the camera to be able to recognize this is an object, this is the foreground, this is the background. So we were concerned about the implementation of that on the software side. And two, our alternative was to just set GPS waypoints and then have it travel along those. But in that gated enclosure, a lot of clubs on campus actually use that as a storage facility. So they moved their stuff in and out of there, they changed the position. So we didn't actually know what the environment would be like the day that we ran the mission until we landed inside. We knew that we would have one landing corridor reserved, but everything else was completely unknown to some extent. So that's why we went ahead and went the manual route so that we had the flexibility of the driver to be able to tackle whatever we could.
All right, good answer. Thank you.
Just visually looking at Vesta and Aura, does Aura actually fit in there?
Let me go ahead and show you.
It looks like you hit a propeller.
Well, yes, as we drive in, we can't hit this, but we can easily push past it.
Even when it's on?
Yes, so the difference, I guess, is that I'm sure somebody from Invictus could answer this a little bit more technically, but how I understand it is that these propellers can be engaged, but until they're actually throttling up, there's no resistance. So they were on, but we could still easily push past them. Is that correct, Ben?
That is correct. As long as the propellers aren't spinning, as long as we don't have it throttled up, it responds just the same as I were to push it, even when the component battery is attached and our motherboard is powered on.
Right, thank you.